All right, let's talk about the secret code that runs our entire electronic world. I'm talking about Maxwell's equations, and they are, without a doubt, some of the most important laws in all of physics. But what if I told you the way you usually see them, well, it isn't the only way, or even the simplest? We're going to dig into this.
So this is what you usually see in a textbook, right? Four elegant, but let's be honest, kind of intimidating equations. They perfectly describe how electricity and magnetism work and how they talk to each other. They're powerful, they're totally correct, but they're hiding a deeper, much more beautiful secret. So we're going to peel back the layers on this amazing idea.
Here's the game plan. We'll start with these familiar four rules. Then, we'll see how Einstein's relativity comes in and just rewrites the whole thing into something much simpler. From there, we'll get to the geometric core, the deepest way of thinking about this. And finally, we'll see how all of these are really just different languages telling the exact same story.
Okay, so let's start at the beginning, right where most physics students do. This is the foundation. And to really get it, you need to meet our two main characters.
First up, you've got the electric field. We call it the E field. And you've definitely felt this. It's that force that just radiates out from every single electric charge in the universe. It's the invisible push and pull that charges exert on each other.
And then you've got its partner, the magnetic field, or B field. Now this one is a little different. It's created by charges that are moving, what we call an electric current. This is the force that makes a compass needle point north, and it's what makes the motor in your blender spin.
And here they are again. When you put them all together, these four equations are the complete rule book. The first one basically says electric fields start and end on charges. The second one, it tells us there are no magnetic charges, no magnetic monopoles. And the last two are the really cool part. They show how a changing magnetic field creates an electric field, and a changing electric field creates a magnetic one. It's this perfect self-contained dance. But believe it or not, we can do better.
So just a few decades after Maxwell laid all this out, this young patent clerk named Albert Einstein comes along with his theory of special relativity, and it just changes everything. It gave us a totally new lens to look at these laws, and what we saw was, well, it was a huge simplification. Just look at this, seriously. On the left are four equations, and on the right, the relativistic version. We just went from four equations down to two. And the most amazing part is that nothing, absolutely nothing has been lost. All the physics from the original four is packed right inside these two. It's an incredible compression of an idea.
So what's the big reveal here? What this new way of writing it tells us is that electricity and magnetism aren't really two separate forces that just happen to interact. No, they are fundamentally the same thing. They are two faces of a single coin we call the electromagnetic field. Whether you see something as an electric field or a magnetic field, it just depends on how fast you're moving.
And you know, this isn't just some mathematical party trick to make things look tidier. Writing the equations like this uncovers a deep, fundamental truth about our universe. That the laws of physics are the same for everyone, no matter how they're moving. It's this profound statement about symmetry, and this simplification is our first major clue that there's a deeper unity at play.
But hold on, because we can go even deeper. Physics didn't just stop with Einstein. In the years that followed, physicists came up with even more powerful mathematical languages. Languages that could express these laws not just as rules about fields, but as fundamental properties of space and time itself. This brings us to something called gauge theory. Now, don't worry about the crazy symbols. The main idea here is that we're looking at something even more fundamental than the fields themselves. You can think of the E and B fields like the wind you feel on your face. Well, this new thing, the potential, it's like the high and low pressure systems that cause the wind in the first place. We're getting closer to the source. And this is the final step. Using the language of differential geometry, the laws become statements about the very shape, the very curvature of space-time. In this language, all four of those original equations get boiled down to these two unbelievably compact lines. The first one, dF equals 0, is just a geometric way of saying there are no magnetic monopoles. The second one ties the geometry of the electromagnetic field directly to the charges and currents that create it.
So, is this it? Is this the simplest, most fundamental way to write down one of nature's most important laws? A lot of physicists would say, yeah, absolutely. We've journeyed from a detailed list of 4 rules to a profound statement about the very fabric of reality.
It's pretty mind-blowing.
Okay, so let's put this all together. We've seen one big idea from James Clerk Maxwell written in 3 totally different ways. You can think of it like a Rosetta Stone for physics, letting us translate between these different levels of understanding.
This table really sums up our whole journey, doesn't it? We started with the standard form, the 4 equations. That's your complete list of rules, perfect for engineers. Then we saw the relativistic form, which cut it down to 2 equations and gave us that aha moment, the unification of electricity and magnetism. And finally, the geometric language gave us just 1 or 2 lines that show this law is really a feature of spacetime's geometry.
And here's the most important takeaway from all of this. None of these versions is wrong. They're all right. The 4-equation version is exactly what you need if you're designing a cell phone antenna. The geometric version, that's what you need if you're a theoretical physicist trying to unite gravity with quantum mechanics. They're different tools, different lenses, each giving us a powerful and unique view of the exact same physical truth.
And that really leaves us with a final thought, doesn't it? This whole journey from something that looks complex to something that is profoundly simple is what physics is all about. And it makes you wonder, if one law can wear so many different faces, what other beautiful and simple truths are still hiding, just waiting to be discovered, inside the complex equations we use to describe our universe?